instead of geometric notions like geometric graphs, geometric simplicial complexes, here I'll talk everything about abstract. There is no positions, there is no metrics, geometric metrics that we want to enforce. So, and this talk is actually about how do we do statistical modeling of functions on the edges. So earlier we saw there is a scalar feature, there's vector features. So this will be particular about vector features on edges. And we will, enforce something called Hodge decomposition into it. So starting from graphs, when you deal with the functions on nodes, you often start from graphs consist of nodes and edges. So this is in fact the simplicial one complex. And if we care about some, triangles, we fill up and we obtain a simplicial two complex. And to later on, when we deal with signals, we want to enforce we want to give some additional orientation structure. So for each simplex, we just choose some reference orientation. For example, edge one, edge E1, I choose it from nodes 1 to nodes 2. Yeah, this is because when I have a signal, for example, these scalar values, imagine, for example, I have this -1.4 on edge 1, 3. It really indicates there is 1.4 unit of flow going in the opposite direction of this reference orientation. So this actually, when you do this mapping from edges to this function space, you assume there's this alternating property. And you can do the same for nodes for triangles. Oftentimes for nodes, you don't have a clear notion of orientation, so this often is ignored. Yeah. And earlier we also saw in many domains there's simplicial complex involved in data analysis, in signal processing, learning, and in computer graphics. And also here we talk about data on edges. So where do we see this? There's a physical, in this physical world, there is a flow type of data, water flow, information flow. And there are other domains in data science. There's, for example, currency exchange. It sounds very far away, but I'll also use this example to show you. And in game theory, ranking with any. So in many domains, there is this. So given this graph, given this simplicial complex, we want to do operations. We want to use matrices. So there is this instance matrix, node to edge instance matrix, indicating how they are connected. Then there is this edge to face instance matrix, P2, indicating how each edge is instant to the face. And then out of this, you could build this graph Laplacian as B1 times B1 transpose. And you could build this one Hodge Laplacian, B1 transpose B1 and B2 B2 transpose. So you see I have different colors really indicating all these two parts of this one Hodge Laplacian really indicates the connections via nodes and via triangles. And this later on affects how we process things when using them. So, so our goal is to do statistical modeling. So imagine, so let's have a look at how people do it in node case when dealing with node functions. So assume there is this random process F0, it's random, and you enforce some zero mean, and you want to really build a meaningful kernel, this K0. It's encodes the covariance between, for example, two nodes, right? How do you obtain this? The existing work started from this stochastic differential equation in red, where this phi L0, it's a differential operator built out of this graph Laplacian. And then you inject the noise on the right-hand side, W0, that's noise. And then if you choose phi L0 to be like a diffusion type of function, to be Matern type of a function, you really obtain Matern and diffusion Gaussian process on graphs, on nodes. So why do we do this? This is because in Euclidean domain, you have this diffusion kernel. So in that small box, you have this bxx prime. It really encodes the distance between two locations, and it has a very well-defined distance. But in graph, we don't have this. So another way to look at this to obtain this kernel is starting from this stochastic differential equation. And then you see there is a beautiful Laplacian. That's how we, do this. Replace everything in the Euclidean Laplacian replace the Euclidean Laplacian by the graph Laplacian. And of course, we could really do the same, and everything is the same. We just replace graph Laplacian by Hodge-Laplacian and replace node function by edge function. We obtain Matrix distribution. But is this really a good thing, right? So when we take another look when viewing Gaussian process, we start from regularization perspective. You check what is the eigenspectrum space. You see that it has this low pass pattern. So here the question is, what does this eigenspectrum mean, right? What kind of low pass you want to enforce? What is low pass here? So this will actually bring out the question: what is the smoothness of the node features and vector features? Also, here we call them node functions and edge functions. And in nodes, when dealing with these node functions, you often have this notion of smoothness, meaning that two nodes, they have similar values, similar scalars and such. But here we will use something called divergence and curl. This really originates from continuous domain. When you check vector fields, you often have divergence and curl notions. And how do we do that? How do we measure them in the graph case, in this abstract graph case? So it's safe to say that instance matrices and Laplacians, they are really derivative operators. So instance, particularly, they are first order. So if you apply this B1 transpose to a node function, it really computes the difference between two nodes. This is really a discrete version of gradient operation. And then if you do its adjoint and apply it to an edge function, you are really computing this net flow at each node, the total inflow minus the outflow. So this is in fact a discrete version of divergence. Yeah. And then another thing is if we apply this B2 transpose on edge functions, and you are really measuring the net circulation in each triangle. So this is some type of a rotation measure of the edge functions. And earlier that's divergent measure of the edge functions. And then if you take another look at the Hodge-Laplacian, it's a composing, it's composed of these first order derivatives and another one. So it's in fact second order derivatives. And And then we want to bring out this Hodge decomposition, particularly on graphs. So Hodge decomposition in continuous domain, when you deal with vector fields, it's actually Helmholtz decomposition, saying that our vector field consists of two parts. For example, I often use this example: electromagnetic waves consist of an electric field and magnetic field. One is divergent, one is rotational. So here we really have this similar idea. Saying that edge functions consist of three parts, and one part is the gradient flow. It's obtained as a gradient of some node function. And another part is the curl flow. It's some curl adjoint operation on some curl on some triangle functions. So this type of flow, they are divergence free. They always enter and they always leave. And the last part, that's a harmonic flow, often obtained as a solution of the Laplace equation, right? And so our idea is, to build a meaningful Gaussian process, starting from the right-hand side, we model gradients Gaussian process, model curl Gaussian process, then harmonic Gaussian process. And why do we do this? Of course, this is because in real applications, we often have data which are really in one of these subspaces, or two of them. For example, when you have these ocean currents, they are velocity fields. If you decompose them, you have two parts, and particularly the curl parts, that's a divergence free. They are always rotating, and this is very interesting for ocean graph. And earlier I talked about that this can be applied to currency exchange. So in currency exchange, there is some rule called arbitrage free. So imagine you have three currencies like euros, dollars, and Chinese yuan. So this rule says if you exchange from euros to dollars, then to Chinese yuan, compared to the direct change from euros to Chinese yuan, it should be identical. So this is an arbitrage-free rule, and if you apply a logarithm, it really translates this into a curl-free condition. And this logarithm is really not accidental. It's related to the actual exponential map and logarithm. And then other domains, you have this in water flows where they have this divergence free. That's actually continuity condition. And in electric circuits, you have this current law and the voltage law. It can be translated into this divergence free and curl free. And among other domains. So this is why we want to model three types of Gaussian processes independently. And earlier we saw that the way to do that is you have some Laplacian and you have some function on it, right? And here is how do we find this Kg, Kc, and Kh, right? So then we have this important thing saying that the eigenspace of the Hodge Laplacian, it really spans the earlier we talked about three Hodge subspaces. So particularly the down Laplacian, it's non-zero eigenspace. It really spans the gradient part. And then the up Laplacian, it's non-zero eigenspace spans the curl parts. And then the zero eigenspace of the total Hodge Laplacian spans the harmonic space. And if you go a step further, if you check these eigenvalues really measure the divergence, what I talked about, divergence and the curl. So they reflect. So this tells you this eigenbasis provides you some basis reflecting either divergent property or rotational property. Right? And so if you take a closer look at these values, you will find, oh, it's matching what we talked about, this divergence free and the curl free. So it's if we take usually in continuous domain, it's it has better visualization. So if we take again this ocean, we build the simplicial complex out of this specific ocean, then we analyze its eigen mode. And then if you check the gradients parts and ordering them based on the eigenvalues, you see that the divergent property becomes more significant. It has more sinks, more sources. And then if you check the up Laplacian, its eigenmodes, the rotational property is more obvious as eigenvalues become larger. So this tells you. And then, so our question was to build this Kg and Kc and Kh again. So we start really from this eigenbasis and we enforce some functions on its eigenvalues. And we obtain this gradient kernel, curl kernel, and then the term family, we have it. So I'll skip this. So it needs, if you deal with the Gaussian process often, then you will be familiar. But just remember these are like functions on this different eigenspace. And we have different independent parameters on these three sets of eigenspace. So then we just compose them, right? We sum them because they are, by definition, they are orthogonal independent. And if you check earlier, we have this one curve in the whole eigenspace, and we really don't know what does the eigenspace mean. Now we know that, we have three curves, and each regulates each eigenspace independent. And then I want to mention a little bit alternative formulation, saying that if you want to encode a good Gaussian process on edges, you start from nodes, you start from triangles, and then you could really use derivatives to obtain another kernel, meaningful kernel, and they are really equivalent to what I talked about. In continuous domain, there are works on this. So let's see some the case applications, how we apply this. So our goal is, to do very simple interpolation in this currency exchange network. So given, for example, 5%, 20%, and we want to interpolate to obtain a fair market being arbitrage free. And we really do this, we do Gaussian process regression, and we learn these kernels. We see that the blue curve indicates the gradient space. It tells, it has a very large gradient component, and the other two are really vanishing. Another part is in this ocean current analysis, we really have this, for example, 5% of the observations. And yeah, by the way, we don't do this in the continuous domain. We do it in simplicial complex domain, and we map them on the edges. And then we go back because we want to show this. And so we can do very good, interpolation. But more than that, what we want to say is, oftentimes you want to obtain the subcomponents, you need to solve a least square problem, solving Hodge decomposition. But now we don't need that because our kernels have these independent parameters, and you can really obtain them in a very simple way. And yeah, this is not, of course, the central goal of doing Gaussian process is to have this uncertainty quantification. We can measure variance of your prediction. The other thing is about water supply networks. They have this, they have data on nodes, they have data on edges. So, and they have this important equation saying that data on nodes is really related, the edge data is really related to the gradient of the node data. So our what we did is we started from a node GP from K0, and we use this equation to build an edge GP using gradient operation. And this intrinsically imposed the equation, physical equation, right? And then it has very good results in comparison to the one that you don't enforce this property. So, and if you see that the learned kernel, so in this water supply network, saying that the edge flow is the gradient of the node data, it tells you the edge flow, it should really have, should really have these gradient components, a lot of gradient components, but not the others. And you see that the learned kernel, it really has this large pose at the low eigenvalue screen, but not at the zero. At zero, it's vanishing. So this is what we did, and so the first question is how do we generalize this Gaussian process to non-Euclidean domain? We took this SDE framework. And then another thing, and more importantly, that's related to my previous work about how do we measure, for example, edge functions, right? In GNNs or in signal processing on graphs, you often have this node data. You have you measure them. You measure their difference, right? Either L1 or L2. So here we really need to check about divergence and curve, really like in continuous domain vector fields. But another thing is this really different, or is this really under a universal framework, right? Node smoothness on node functions or smoothness on edge functions. In fact, they are universal in the sense that you measure node functions in terms of its cophase, in terms of its edge connection. So you measure edge functions in terms of its connection Y nodes and in terms of its connections Y common triangles. So this is, you always use this first order differential. This is in fact on topology on graphs, the reflect. And then what is a good GP? You want to encode this edge dependence. Also, you want to have this Hodge decomposition included. And also there are other works like how do we do node edge triangle joint GP. And then we often took ideas from continuous domain. We check in continuous domain when dealing vector fields on Euclidean domain on manifolds. Yeah, there are really, in fact, concurrent work with us. Yeah, thanks. That's my talk. In fact. Yeah.